you very much, Rudradi, for the opportunity. Thank you very much for the opportunity to speak in this seminar. Actually, I'm very happy to talk about this today in this seminar because what I'm going to talk about today arose after a seminar talk, after an online seminar too. And during the questions, after a question of Gustavo, we realized that what I had been speaking about in that seminar could be vastly generalized to the context I will be using here. So I guess I will start by recalling what I was talking about in that other seminar, and then I will spell out the result with Gustavo, and then I will try to comment on the proof or whatever, okay, as time allows. So let me once and for all write down some assumptions. So K will denote a ground field, which will be perfect. This will only be used once, but in a crucial way, so we can't avoid this hypothesis. T will be an additive category. Regarding the notation for this category, you will guess that it will often be a triangulated category, right? But for the moment, it will be an additive category. Since K is a ground field, K acts on T and so on. So everything is enriched on K vector spaces. This category will be small. And it will be idempotent complete. And it will have finite dimensional morphism sets, okay? The Hom vector space between any two objects in this category will be finite dimensional. And we will also have a self-equivalence of T, which we call the suspension factor or translation. Depending on your background, you will like one terminology or the other, right? So our idea is that we're going to study triangulated structures in the category T with suspension factor sigma. So let me recall what's an algebraic triangulated category. We say that an algebraic triangulated structure on T an algebraic triangulated structure on T is given by a pair given by a DG category, small, and an equivalence between the category T and the derived category of compact A modules, right? So this means compact. Of course, this category is canonically triangulated. It's a small triangulated category. So through this equivalence, we can transfer the triangulated structure on the right to the left, right? So we have a real underlying triangulated structure on T through this equivalence. If we have fixed the suspension factor, then we may want this equivalence to be compatible with the suspension factor on the left and the suspension factor on the right. If we haven't, then we can also transfer the suspension factor on the right to the left. Okay, what are the equivalences between these algebraic? Well, under these circumstances, we also say that A is an enhancement. An enhancement of T. This is the terminology of von Delta-Pranoff. So we have equivalences between enhancements, and they are called Morita equivalences. Morita equivalence between DG categories is a DG factor which induces an equivalence on the right categories on compact objects. Okay, and we say that two DG categories are Morita equivalent if we have a zigzag of DG of Morita equivalences between them. So we not always we can construct a direct one. Okay. Something else. We say that our category T is finite, additively finite. If it has finitely many isomorphism classes of objects of indecomposable objects. Finitely many decomposables. So the hypothesis on T implies that any object factors as a direct sum of indecomposable objects with local endomorphism algebra in an essentially unique way. And we only want to have finitely many of those in the finite case, up to isomorphism, obviously. In this case, T is equivalent to the category of projective modules over lambda, where lambda is the endomorphism algebra of an object T, which consists of one indecomposable for each isomorphism classes of indecomposables, right? So this is the complete list of different indecomposables in T. And if T is triangulated by results of Wright, if T is triangulated, then lambda is a basic Frobenius algebra. Well, the results of Wright imply that lambda is self-injective, but here we take only one iso class for each indecomposable. So this implies that lambda is basic, and then being self-injective is Frobenius, which means it has a trace like square matrices and so on. These are much better properties because they are inherited by tensor products and so on. In particular, the enveloping algebra, this we will use, will also be Frobenius, so it will be self-injective and so on. This is a result which was published in 2 years ago, which says the following. Assume the necessary hypothesis for T to be triangulated. Okay, so T will be a finite category, finite additive category with lambda basic Frobenius algebra. Then we have the following. First, T has an enhanced triangulated structure in the previous sense, the sense of Mondal-Kapranov. If and only if the third CCG of lambda as a bimodule over itself, here we have the enveloping algebra, parametrizing bimodules, which, as I said, it's also Frobenius. So the third CCG is well defined, everything. So T has an enhanced triangulated structure if and only if this is stably isomorphic to an invariable lambda bimodule. Okay, so we have a complete characterization of when we have an enhanced triangulated structure. Moreover, we can say something about the suspension factor. The suspension factor in the previous circumstances, if one holds the equivalent conditions in one hold, then the suspension factor is must be isomorphic to the tensor product with the inverse of I. Okay, so we have not many choices. We have more than one choice because here we say stably isomorphic. We may have different bimodules which are stably isomorphic. So we have different choices of sigma. In practice, there are examples of that, but not many. They have this restriction. And then once we have fixed sigma, if sigma is given, any two enhancements of the pair T sigma are Morita equivalent. So we characterize when such T finite category has an enhanced triangulated structure. We characterize which are the possible suspension factors. And once we fix one suspension factor, the enhancement is essentially unique up to Morita equivalence. And we should comment also on a result of Hanihara, which was published about the same time, which says that under the same circumstances, this has an ordinary triangulated structure, not enhanced, if and only if the condition above holds. So the very same conditions, this very condition, okay? If and only if this condition holds. Yet, we do not know whether all triangulated structures are algebraic. Why? Because in principle, Hanihara doesn't establish a relation between this property and the exact triangles in a given triangulated structure. So this is kind of indirect. So if this holds, if T has an ordinary triangulated structure, then only one of them is algebraic once we fix the suspension factor, but there may be other ones which are not algebraic. This is, I asked this question to Hanihara and didn't find an answer. Okay, so how can we generalize this to a wider context? Because, I mean, if one is not very much into representation theory, finite triangulated categories is not something one is often looking at, okay? So I'm going to speak about the generalization of this, which is still also relevant mostly in representation theory, but well, at least there are examples, there are many examples for which the theorem I will talk to you about next holds, but it applies, but not the previous one. So I must recall what an cluster tilting object is. So and cluster tilting object T of T with suspension factor sigma is an object such that the following property holds. The harms from T to the suspensions of another object vanish for all values between 0 and n. Okay, so here we have n. If and only if x belongs to the additive completion of T. So this is the category which is obtained from T by taking the direct sums, direct sums, and so on. Okay, the additive completion. And also if and only if the dual property holds. Okay, so some facts. First fact, which holds in whenever we have an n-cluster tilting object, is that T generates T, the category, meaning first, for this, of course, this is thought for the case when this is a triangulated category, which is when it has more implications, but we really do not need T to be triangulated and sigma to be the suspension factor for this to make sense, right? We only need a category and a self-equivalence. And T generates T in the usual sense, right? So any non-trivial object of T gets a non-trivial map from an object in the from T. And more things. The previous notion of finiteness is equivalent to the existence of one cluster tilting object. So we want to generalize everything from before to the case where this can be anything, okay? And we have the following theorem together with Gustavo. So assume that T is algebraic. T is an algebraic triangulated category. With an unclustered tilting object. Then T has a unique enhancement up to Morita equivalence. Okay. So there are many examples of categories satisfying these assumptions, although I would be very grateful if you didn't ask me anyone, because they arise mostly in representation theory, and I consider myself a homotopy theorist, so I may remember some of them, but I would have to struggle to remember some of them which do not fit in the conditions of the previous theorem. But there are many, okay? So this T here need not be finite. Many things can happen here. And well, we have a kind of result which somehow resembles the last point of the previous theorem, okay? Because we have uniqueness of enhancements, but our assumptions are stronger because we have started with T, an algebraic triangulated category. So we already assume that we have fixed a suspension factor and a class of exact triangles for which we have oops, sorry. Yeah, we have more assumptions, right? And you may wonder how this second theorem, the theorem with Gustavo that I wanted to promote today, is related to this previous theorem here. the thing is that we have to go through a world where we can generalize this, and then we will obtain this theorem as a corollary. And this is where I'm trying to head now, right? For this, I have to speak a little bit of n-angulated categories in the sense of Geiss-Keller-Oppermann. So, n-angulated categories. An angulated category is a sort of higher triangulated category, but not in the sense that we homotopy theorists think of. So there are no higher categories here. Our categories will be ordinary. The thing is that we will have something resembling triangles, but which will be longer, right? So what do we need? We need a category. Equipped with a suspension factor. Suspension factor, same as before. And a class of diagrams that we call n-angles. Although we should call them squares, pentagons, or whatever, right? So we have x1, x2, ... up to xn, and then the suspension of the very first one, satisfying some actions in such a way that we recover triangulated categories for n equals 3. Okay. And how do these kind of categories show up? Well, the theorem of Geiss-Keller-Oppermann says that if T is a triangulated category, and T is an n-2, mind the number, n-2 cluster tilting object, then the additive completion of the n cluster tilting object is n-angulated with suspension a power of the suspension of T. Okay, so we can find the usual way of getting n-angulated categories is as subcategories, full subcategories of triangulated categories with n-cluster tilting objects, right? And where do we get n-angles from? The thing is that we get n-angles from exact triangles too. So the typical thing that you can imagine is one of the actions of n-angulated categories is that whenever you have a map in F, we should be able to complete it to an n-angle in this way, okay? To a complete sequence which becomes an n-angle. And they have, what they do is that they take the mapping cone in the triangulated category of this first map, and they call it funny notation x.2.5, and this is well, the usual notation for a map to the suspension plus 1. This is an exact triangle in T. And then this object here, because of the hypothesis of of an cluster tilting object, and so we can embed it in a canonical way in an object here. Okay, all these objects I'm going to draw in yellow belong to F. Okay, so these things belong to F, and of course the arrows. This one here, this other one here, and this map here is a map that that T somehow regards as an injection. Okay, and then we take again the mapping cone of this map in the triangulated category, and here we get an object which should be called 3.5, which is part of an exact triangle in T. Again, we embed x 3.5 in an object x4, which belongs to F. So this is something which T regards as an injection. And we keep on doing this all time. And the thing is that it stops because of the properties of an n-cluster tilting object. So we have here x n minus 1.5, x n minus 1.5, x n minus 1, this map here, which T regards as an injection. We take the mapping cone, and this mapping cone now belongs to T. Okay? So now all of this belongs to T, and since we want a map, since we need a map from xn to the n minus 2 full suspension of x1, the map we have to take is the composite of all this, right? This is a map which goes to the n minus 2 shift of the target object, because here in the middle, we have given n minus 2 steps, if you count them well. So this is the structure. And okay, so now we're going to state a theorem like this one for enangulated categories. And we're going to see that our theorem for triangulated categories with a cluster tilting object is a corollary. Why have I presented this theorem first? Because this is the main motivation, right? So triangulated categories were way more important than enangulated categories, as this is a typical case that we have a result which is only on triangulated categories, but for its proof, we need to use enangulated categories and things related to them. So we need the notion of algebraic enangulated categories, okay? So now we will give a definition which somehow is due to us, but it extends the usual notion of algebraic triangulated category due to Bondal and Kapranov. And we take n greater or equal than 3, and then a DG category, a small DG category. We say that it is n-angulated if the Yoneda full embedding of the zero-dimensional cohomology of A into the derived category of compact modules. So these are compact modules, and this inclusion here, it's like the inclusion of projective modules. So if this is the inclusion of an n-2 cluster tilting subcategory. Okay, So we have called about cluster tilting objects, not about cluster tilting subcategories. But the general notion of a cluster tilting subcategory, it just encodes the properties of the category of the additive completion of an n-cluster tilting object. So it's not really worth to define the general notion. So it's something which satisfies the same formal properties within T as the additive completion of an n-cluster tilting object whenever we have them. Again, beware that for n-angulated categories, we need n-2 cluster tilting objects. There is a shift there. We can't avoid it. We have to live with it. So now we can define enhancements, okay? An enhanced n-angulated structure on a category F is an equivalence is given by pre-n-angulated DG category A and an equivalence between F and the zero-dimensional cohomology of A. Okay, so again, if we have fixed a suspension factor on F, then we want this equivalence to be compatible with the suspension factors on the left and on the right. On the right, we have one because I forgot to mention the previous theorem of Geiss-Keller and Oppermann applies actually to any n-2 cluster tilted subcategory of a triangulated category. So in this case, H0 phi is n-angulated by the previous theorem. Okay, so this one carries, it has a suspension factor, which will be the n-2 fold suspension, the restriction of the n-2 fold suspension in the derived category. And it has a class of exact n-angles and so on. We can transfer to F the class of exact n-angles if this equivalence here is compatible with suspensions. If we don't have a predefined suspension on F, we can also transfer the suspension from the right to the left and so on. Okay, and as usual, we call A to be the enhancement of F. You'll see that there are some differences between this and the previous definition, right? Because when we recalled what an algebraic triangulated category is, we didn't make any reference to the zero-dimensional cohomology of A, right? We wrote down the derived category of compact object. The thing is that when A is pre-triangulated, in the sense of Bondal and Kapranov, then this and the zero-dimensional cohomology of A are the same, right? So this definition really generalizes the definition of the previous one, the definition of Bondal and Kapranov in the case n equals 3, okay? This gives you the classical definition. And what else? Now we have to define the right kind of equivalences we're going to consider here, and they are the most naive ones, the quasi-equivalence. So a DG factor is a quasi-equivalence if the induced factor in cohomology is an equivalence of graded categories. Okay, and two categories are DG or quasi-equivalent if there is a zigzag of quasi-equivalences between them. Okay, so now Now we can state the theorem, which will also actually be very much the same as this one. So probably we'll copy the page and copy and change whatever we have to change, if you allow me, if I manage to. As you can see, I'm not very technologically skilled. Okay, here we are. By the way, I didn't mention it before, but as a consequence of the theory of Geiss-Keller-Oppermann and so on, if the category of projective modules or a finite dimensional algebra is n-angulated, then lambda is again for lambda basic algebra, basic finite dimensional algebra, then lambda is Frobenius. Okay, this is due to Geiss-Keller-Oppermann extending the previous result I mentioned by Freud. So we are completely, I mean, we're not making any strong hypothesis if we already start with a basic Frobenius algebra. And the thing is that it has an enhanced n-angulated structure. If and only if the MCCD is stably isomorphic to an invertible lambda bimodule. We should call this F maybe, because we are distinguishing between the triangulated category and the Frobenius, and the cluster tilting category. Then the suspension factor, if there's any one, it should be the inverse of the previous one. And once we fix the suspension factor, then we have an essentially unique enhancement, because any two different ones are quasi-equivalent. This is the theorem with Gustavo. So we have a similar characterization to the previous theorem for finite triangulated categories, but now for n-angulated categories. This should be blue too, to stress the differences. And now, how do we deduce the theorem I really want to stress from this one, right? This theorem with some real triangulated categories from the theorem on n-angulated categories. Well, if we take T, which is a triangulated category, we can take an algebraic triangulated category. Recall that the hypothesis of that theorem I want to prove is that we already start with an algebraic triangulated category. We can actually take an enhancement which is pre-triangulated. So the derived category of compact objects is equivalent to the zero-dimensional homology. So this is a pre-triangulated enhancement. If F is an n-2 cluster tilting subcategory, then the full subcategory sub DG category AF spanned by the object of F is an n-angulated enhancement of F. So yeah, whenever we have an enhancement of a triangulated category and an n-2 plus rotating subcategory, we have a canonical enhancement of F as an n-angulated category by restriction. And conversely, if we start just with this, we can recover the whole A, because A is the Bondal-Kapranov pre-triangulated whole of AF, right? So if since A is determined by AF, as long as we have that we can only have one AF, which is what the third part of the previous term says, then we have that we can have at most one A. So this theorem here becomes corollary, or if actually giving you the proof. Okay, I actually do not have much time to start talking about technicalities, but the idea for the proof of this theorem, if you've ever heard me speaking about the previous one, about the triangulated one, maybe you know that what we do here is trying to recover an A infinity per triangulated model for the category. So let me go to the previous one, right? We start with T, we have this condition, and from this we try to recover an A infinity multiplication on the, not on T, but on the graded version of T, which is constructed from the suspension factor. And we see that we can do it in an essentially unique way by using abstraction theory, right? The difference here is that essentially that when we have a pre-angulated enhancement, I have only mentioned the zero-dimensional cohomology, but in fact, the whole cohomology of A is concentrated in degrees multiples of n. So it's an algebra, graded algebra with gaps, right? We have cohomology in dimension 2, n, 2n, 3n, minus n, minus 2n, and so on. So when we want to have, when we want to put there an infinity model, right? So most operations in the infinity algebra are going to vanish. Essentially, all mn's are going to vanish. I mean, all mi's are going to vanish except for those which are divisible by n minus 2. And then we have essentially the same techniques as in the previous case, some abstraction theory, moduli spaces, homotopy moduli spaces, and spectral sequence, vanishing, and essentially uniqueness. So yeah, I think I will be done with this. Thank you very much for your attention.
Thank you, Fernando, for the wonderful talk. Can we all please unmute ourselves and thank the speaker? Okay, so if you have any questions for Fernando, please unmute yourself and ask your questions, or you can put them in the chat. There was a question from Antonio. Oh no, yeah, I think, yeah, it's been answered in the chat itself. Yeah, I had a sort of a silly question. Fernando, I mean, of course, you're aware of the theory of algebraic versus topological triangulated categories. And I think you yourself have a result with, I think, Niels Strickland and Stefan Schwede of giving examples of triangulated categories that are not neither algebraic nor topological. I was wondering if, first of all, that algebraic topological business can be carried over to n-angulated categories, and then do we have examples of higher n-angulated categories that are neither algebraic nor topological? I'm sorry, this is not exactly related to this talk, but since we're talking about n-angulated, I thought about this.
Yeah, this was addressed in a paper by Gustavo actually and some of his collaborators. I don't remember by heart now the list of.
Peter Berg and Marius Tauler.
Sorry?
With Peter Berg and Marius Tauler. So I'm Gustavo. Hi, Mark. Hi, Fernando.
Ah, Gustavo, you're here. Okay. Nice to see you. Yeah, okay. So yeah, but actually they show that some example is not algebraic because as far as I know, these enangulated categories do not show up in topology. I've tried to look them up. No, I haven't found any enangulated category in a purely topological example. Say.
Okay.
Yeah, I don't think any example which is topological is known, as far as I know.
Okay.
Yeah, yeah.
Okay. Thank you. Okay, do we have any more questions for Fernando? Let me see the chat.
I see the chat.
All right, it doesn't look like we have any more questions incoming. Yeah, in that case, let me thank all of you again for coming. The video of this talk will be uploaded to the YouTube site of this seminar series. I have already had requests from people asking me to send in the link. So yeah. So next week we have Luca Ball from the University of Regensburg speaking. And the week after that we have Paolo Stellari, I think. Okay.
Okay, thank you very much.
Okay. Yeah, thank you, Fernando.
Grazie, Fernando.
Bye.